In this video, I want to provide a proof of the fact that the beta distribution is conjugate to a binomial likelihood. I know in the last video I provided an intuitive proof of this, but here I want to provide a complete and mathematically correct proof. So to start off, we're going to start off by writing down our posterior density, so the probability of theta given our data x, and x here in the case of a binomial likelihood is the sum from I equals 1 to n of individual Bernoulli trials, so the results of individual Bernoulli trials, which I've called xi here. And we know that the posterior is equal to the probability of the data given theta, which is the likelihood, times the probability of theta, all divided through by the probability of our data, just the probability of x. And we remember that the numerator here is essentially the same thing as the joint probability of x and theta. And then what we do is we notice the fact that the joint probability of x and theta, the joint distribution, is essentially related to the denominator here. If we integrate out across all range of theta, then we convert the joint distribution into the marginal distribution of x, which is this term here. So we can rewrite the denominator as just the integral of the numerator. So it's the integral from theta equals 0 to theta equals 1 of the joint distribution, the probability of x and theta, integrated across all theta. So if we can work out the numerator, which we're going to do just using this first part of Bayes' rule, then if we integrate over that over choice of theta, then we can get the denominator, the marginal probability density of our data. Okay, so in order to start here, we need to write down our likelihood function, so the probability of x given theta, which we know is just equal to nx, where it has its sort of normal meaning here for NCR, times theta to the power x, times 1 minus theta to the power n minus x. So that's our binomial likelihood. If we write down our prior here is just that the probability of theta is equal to the beta distribution. And I'm going to write the beta distribution in a slightly different form. I'm going to write it using the gamma function. It's equal to gamma of a plus b divided through by gamma of a times gamma of b, all times theta to the power a minus 1, this sort of first parameter, times 1 minus theta to the power b minus 1. Okay, so these are our two terms of our numerator now. If we multiply them together, we're going to get the joint probability. But before we do that, I'd quite like to do something with this nx term here, because at the moment it doesn't really look that sort of friendly compared to everything else there. So in order to change this, we're going to note that nx, what this actually stands for is it's a shorthand for n factorial divided through by, in this case, n minus x factorial times x factorial. And we also note that the gamma function is essentially the continuous equivalent of the factorial function. And we know that the gamma function has the property that the gamma of a plus 1, alpha plus 1 here, where alpha is an integer, is equivalent to alpha factorial. So what we can do is we can rewrite this nx term here just using the gamma function. The numerator just becomes the gamma function of n plus 1. The denominator just becomes the gamma function of n minus x plus 1 times now the gamma function of x plus 1. So putting this all together now, we can derive the joint distribution, so the probability of x and theta, the joint distribution, is equal to gamma of a plus b times gamma of n plus 1 times, or divided through rather, by gamma of a times gamma of b times gamma of n minus x plus 1 times gamma of x plus 1. So that's a sort of whole sort of constant term that we just sort of swept under the carpet in the last video. But then what we have is just exactly the same as what we had before. So now we're just going to have theta to the power, it's going to be a plus x minus 1 times 1 minus theta to the power, in this case it's going to be n plus b minus x minus 1. So that's the joint distribution. Now in the next video what we're going to do is we're going to integrate over this rather foreboding looking joint distribution to help us to derive the denominator. So this is already the numerator of our Bayesian formula. To get the denominator and hence to get the posterior distribution, we need to integrate over this over choice of theta. And actually it's not as bad as it looks. There is a trick that we can use that makes it very simple to actually do this.